In this section, we're going to approximate the binomial distribution to the normal distribution. So here I've got a random variable x which follows a binomial distribution with 20 trials, and the probability of success on each trial is a half. And what we're going to do is we're going to try and approximate this to a random variable that's normally distributed. So I've drawn a bar chart to represent this binomial distribution to try and help us think about what the distribution looks like. And remember, along the horizontal axis I've got x, the specific values of x, and that are possible from 0 up to 20, and the height of each bar represents the probability of getting that x value. So for example, the height of the 13 bar tells me what's the probability that my random variable x is 13, i.e. getting 13 successes. So you can see that's just under 0.08. Well, you might have noticed that this bar chart sort of has the shape of a normal distribution. Let's draw that over the top. So this is what a good approximation to this bar chart would look like. And you can see that this red line does look like a normal distribution curve. Well, it turns out that what we're going to do is we're going to approximate x to a random variable which is normally distributed. And let's call that random variable y. So y's distribution curve looks like this, the red line. And the mean of the normal distribution, well, you can see that 10 is clearly in the center of this normal distribution. So the mean of the normal distribution is going to be 10. And we'll look at the formula for calculating variance, but I know that the variance of that normal distribution curve is 5. So our aim now is to use this red curve, this normal curve, in order to find approximate probabilities for the binomial distribution. So just as an example, let's say that we want to find out what's the probability of x, our binomial random variable, being 13. Well, obviously we could use our calculator to work out what this probability is, and we've already worked that out. It's the height of this 13 bar, just under 0.08. But let's suppose that we want to force ourselves to use this red curve to find an approximation to this probability. Well, you might be tempted just to say, well, surely that's just the probability of y being 13. Well, the problem is, because y is a continuous variable, if we tried to work out the probability of y being 13, that would actually be 0. And the reason why is, to find a normal probability, you work out the area underneath the curve. And the area underneath the curve here at just 13 is 0 because the width, I've not drawn a rectangle. So for a normal random variable, the probability of getting a specific value, so just 13, is always 0. So what we're going to do instead is we're going to use a process called continuity correction. And continuity correction is called that because it basically allows us to convert from a discrete distribution to a continuous distribution to approximate probabilities. So the way continuity correction works is we're going to draw a rectangle or a bar around 13, and we're going to make sure that the width of the bar is 1. So this bar goes between 12.5 and 13.5. And because we've made the width of the bar 1 and the height of the bar is just the probability of x being 13, if we were to work out the area of this bar, we would do 1, the width, times by the height, which is the probability of x being 13. So we just get the probability of x being 13. So we know that this is the area of the green bar. So the problem then becomes, how do we use this red curve to estimate the area of this green bar? So what we're actually going to do is we're going to say that this is approximately equal to the probability of y being less than 13.5 but greater than 12.5, so between 12.5 and 13.5. And remember, to work out this probability, we'd work out the area underneath the normal curve between 12.5 and 13.5. So if we were to do that, we're going to work out this area, and we would do this whole area here underneath the bar, underneath the red curve, sorry. and we would come up with this area here. Now you can see that this is a pretty good approximation. We've got most of the bar, however we've got this extra bit here and we've missed out this bit of the green bar here, which is why it's only an approximation. So at this point it's worth mentioning what are the conditions that make this approximation good. And basically the question is, when does the binomial distribution, when do the bars look similar to a normal curve? So we just did it with n is 20 and p is 0.5, and you can see that the normal curve fits quite well. These bars that we were drawing in are approximately going to be equal to the area underneath the red curve. They fit well. Well, let's see what happens when we increase n. If we increase n and make n really large, you can see that the difference between the bar and the area underneath the red curve decreases. It might be easier to see that if we do a really small value of n. Here you can see that's not a very good approximation because the normal curve doesn't fit very well to the bar graph. There's going to be big gaps when we approximate. So that tells us that larger values of n give us a better approximation. So our condition is going to be that n has to be large to do this approximation. Let's have a look at the effect of p then. So let's say n is 30. Let's see what happens when we change p. So if we have a really small value of p, it's not going to be a very good approximation because all the binomial probability is skewed towards the left. So the small values of x have a big probability. It's not very symmetrical. So it turns out that the best approximations are when the binomial distribution is symmetrical, because the normal distribution is symmetrical. And that means that p has to be close to 0.5. And again, you could go to a large value of p, and as soon as we get to a large value of p, it's not a very good approximation. So hopefully this shows you that in order to make the binomial distribution look like the normal distribution, you need large values of n and small values and p close to 0.5.